All right, in this video, we're going to talk about an example of population growth using a contrived example of fruit flies, okay? So let's say, hypothetically, that a population of a certain type of fruit fly doubles every 20 days, okay? So you got them in some sort of ideal environment in a lab somewhere, and they're reproducing and multiplying, and every 20 days the population size doubles. It says complete each of the following if you begin with 6 fruit flies. So you just take 6 of them, put them in this environment, and they start doubling. So after 20 days you'd have 12, and after 40 days you would have 24, and so on, okay? So here it says, the first part is express n as a function of t in days. So we're going to define time to be in days. I said in a previous video that that's usually in years, but it is whatever the units are on our time, okay? So n as a function of t in days. So we start off with our formula, n of t equals n sub 0 e to the kt. All right, and what we know is that we have an initial value of 6 fruit flies, so the n sub 0 is 6 right off the bat. We also know that after 20 days, so t being 20, we know that the population will double, okay? And so we know that n of 20 is going to be double the initial value, right? If that makes sense. So the initial value is 6, but the 6 isn't really necessary to get the formula. If you double that, it occurs after 20 days. So n of 20 is 2 times n sub 0. Now I'm going to go ahead and make a substitution here. I'm going to substitute the 20 in for the t, that represents our number of days, and the 2n sub 0 in for the final amount after the 20 days. So we'd have 2n sub 0, that's this side, equals n sub 0 e to the k times 20. That's what you get when you plug in the 20, okay? Now to solve this for k, because k is really the only thing I don't know, I could divide out the n sub 0, which we know the n sub 0 to be 6, but again, that's not going to be necessary for finding the k value, which represents our rate. So I'm going to divide out the n sub 0 from both sides. And that gives us 2 is equal to e to the 20k, right? K times 20 or 20k. And so now I'm going to solve this exponential equation for k by utilizing the natural log, okay? If I take the natural log of both sides, natural log of 2 equals the natural log of e to the 20k. And of course, the natural log of e to something is just that power. And so we have the ln of 2 is equal to just 20k. The natural log and the e kind of cancel each other out there. And then I divide both sides by 20 to find the value for k. So our value for k then is simply 1/20th the natural log of 2. If I wanted to find a decimal approximation for that value, I could type in ln2, close parenthesis, divide by 20, and I get approximately 0.034657. Maybe I'll round it off there. There's a few more decimals, but I'm not too interested in all the details there. Okay, so there's my k value. All right, now, so that tells me my final function is going to include this decimal as my k value. So we're going to have n of t equals 6 times e to that power 0.034657 t, right? This would be a valid model to represent this situation. Second question says, what will the population be 50 days from now? So in that case, we want to plug in 50 into our model and see what the output is, okay? So n of 50 equals 6 times e to the 0.034657 times 50 power. So the 50 goes into the exponent there, and it's just a matter of calculating that. 6 times e to the 0.034657. Now there's going to be a slight rounding error here, but I'm okay with that. I'm really just interested in getting the process down, times 50. And that should be, if you calculated it correctly, 33.9405, roughly, okay? Now I would put that as 34 fruit flies, although it's possible they didn't get the 34th fruit fly until after day 50, but I'm going to go with 34, okay? So we're going to say 34 fruit flies. Okay, so that's how many fruit flies you would have after 50 days. Here it says, how many days will it take for the number of fruit flies to grow to 1,000? So you fill this environment, up to 1,000 fruit flies, let's say. How long will it take? Well, that's going to be your final value. So we're going to solve by putting 1,000 in for the number n. That equals 6e to the 0.034657 t. We're going to solve this for t. Now to do that, the first step is going to be to get rid of the 6. So I'm going to divide out the 6 on both sides. And of course, 1,000 divided by 6 is a decimal, of course, or fraction. It's a repeater. It's 166.6 repeating. And that equals e to the 0.034657 t power. Again, similar to what we did over here, I'm going to use the natural log to get rid of this exponential. Take the natural log of both sides. I get the natural log of 166.6 repeating equals, now when I do the natural log of the right, you already know that the natural log and the e will cancel off. So I'm actually going to do 2 steps in one here and just give you the exponent, 0.034657 t. Now to solve for t, I'm going to divide both sides by this decimal, and that should give us a pretty good approximation of the number of days. Okay, and so I'm going to take the natural log of my previous number, divide that by 0.034657. That gives me about 147.6 days. All right, so t is approximately 147.62. So we'll call that about 148 days. Okay, so about 148 days. So after 148 days, it's I don't know, what is that? That's about 4.5 months or so. So after 148 days, the population will grow to about 1,000 fruit flies. Okay. So again, the main idea here is that you use this growth formula. You're going to use the given information to figure out what your n sub 0 is and what your k is, which is the rate. Okay. And then from there, you can answer the questions once you've established this model. Now, one other thing I did want to point out is that even though this k value is 0.034657, your textbook may, and my math lab, may want you to use this as a, what would that be, 3.5 roughly percent increase. Whereas in actuality, the percent increase is e to that power minus 1. So it'd be e to the 0.034657 minus 1 is about a 3.526% growth rate. Okay, so the growth rate is a little bit different than what my math lab will say, but you'd want to put that in percent form to use a growth rate. So the actual growth rate is a 3.526% increase per day. Okay, 3.5% per day. Yeah, so it's a little bit off from that, but it is very close. In fact, they round to the same 3.5. But that doesn't always happen that way. So they are off just a little bit. Of course, I did e to that power minus 1 to get that actual percentage growth rate.